Hello and welcome. In this course, our focus is thermal integrity problems within the 3D heterogeneous integration system, a critical topic as design grow more complex and densely stacked. We will start by exploring the foundations of thermodynamics, the key concepts and physical principles that govern heat behavior in electronic systems. Then, we'll examine how thermal integrity challenges evolve across multiple scales in 3D IC design, from device level to system level, highlighting the unique problems introduced by vertical integration. And finally, we will apply these insights to a real-world example, a multi-die HBM system or high-bandwidth memory system. We will walk through its thermal design analysis and unpack the decisions that ensure the system reliability and performance. In the world of multi-die system design, thermal integrity isn't a one-size-fits-all concern. It looks very different depending on the persona you're asking for. For example, for device-level engineers, their focus is on the self-heating effects and how elevated temperature can compromise the long-term reliability at the transistor level. For firmware and software engineers, they want to prioritize the dynamic thermal management algorithms using real-time data from on-chip thermal sensors to regulate performance and prevent overheating of the system. For physical design engineers, they pretty much worry about joule heating in interconnects, how the current flows through tightly packed metal layers that can impact the layout decisions and circuit performance. Finally, for system engineers, they probably think holistically about cooling strategies, from air and liquid cooling systems to the integrated thermal protection mechanisms across the entire multi-die package. As device power delivery surges and package dimension expands, the thermal integrity becomes a shared priority, essential for preserving performance, reliability, and system integrity. So, what is thermal integrity? Thermal integrity is the capability of a semiconductor device or integrated circuits to a couple of aspects. It includes the dissipating heat efficiently to prevent thermal buildup, to maintain stable performance under varying thermal conditions, and to ensure long-term reliability by mitigating thermal stress. To ensure the thermal integrity of multi-die system design, the designers typically have to apply several techniques. First, they have to think about thermal-aware floor planning and placement, which strategically positioning high-power blocks to minimize heat concentration of the entire stack. Secondly, they use thermal vias, heat sinks, and spreaders across the design to provide effective physical pathways for heat dissipation across layers. They can also use dynamic thermal management or DTM approach by implementing adaptive controls like throttling, clock gating, and power scaling based on real-time thermal sensor data. Now, let's begin by reviewing some fundamentals of heat transfer modes. We typically are looking at three primary modes of heat transfer, each contributing to temperature changes within physical systems. First, conduction-based. So, in conduction-based heat transfer, Heat moves from a region of high temperature to low temperature through direct physical contact. This process occurs via the molecular vibration without displacement of particles. The common in solid-state circuits where the heat travels across materials like silicon and copper, they always come up with conduction-based heat transfer. Second one is convection. So the heat flows from a solid surface to a fluid, liquid or gas due to the bulk motion of the fluid. This type of convection plays a crucial role in cooling systems, especially with liquid cooling in multi-die packaging system. Finally, radiation is the energy emitted in the form of electromagnetic waves driven by the bodies of temperature. Unlike conduction or convection-based heat transfer, no medium is required for radiation, which can occur even in a vacuum. Understanding these modes sets the stage to evaluate heat behavior of complex multi-die system design to optimize their thermal integrity. Now let's look at the physics behind conduction-based heat. We understand that the temperature behavior by using an analogy of the famous Ohm's law in electronics here to show you. So in Ohm's law, it states that the current flow from a source to the destination in a circuit can cause a voltage drop. The ratio between the drop and the current is described as the electrical resistance of the circuit path. Resistance depends on the material geometry and the resistivity properties. Now, in a similar way, if we look at Fourier's law in thermodynamics, it states that the heat energy flow through a medium can cause a temperature change. The ratio between temperature change and the power source is described as the resistance or thermal resistance of the heat conduction path. Thermal resistance depends on the material geometry and thermal conductivity property in a very similar way to Ohm's law. Now, let's see how these thermal principles affect transistor-level thermal integrity problems. As the current density increases, the junction temperature of the transistors also increases. In planar CMOS technology, you can see that the heat paths are relatively manageable because of a lower current density. But in the modern FinFET CMOS technology, the vertical structure that introduced can spread the heat in 3 dimensions. The next generation gate-all-around devices pack even more nanowires to complicate the heat conduction even further. When the devices are not active, the leakage power can also introduce heat inside these devices. And the thermal coupling in these 3D transistors is definitely so critical to be understood. Now let's look at the thermal integrity through the lens of multi-die system. When stacking dies, each packed die has millions of transistors, creating vertical heat flow paths. A die near the bottom of the stack can heat up a die directly above it, creating some hidden hotspots. These stacks aren't homogeneous. We are dealing with copper wires, silicon, solder bombs, copper pillars, and more structures. So accurate thermal analysis depends on understanding all of the material properties of these components. And remember, the thermal conductivity can be anisotropic, meaning that the heat behaves differently along the X, Y, and Z directions. Such directional behavior is shaped by routing layout and via placements, making it a design variable, not just a physical fact. To model these complexities, we typically resort to finite element analysis approach, or FEA. So FEA translates physical structures into mathematical models. It will account for geometry, material properties, and boundary conditions. Also, we typically use meshing to break down the multi-die layout into countless elements, each representing a tiny chunk of the whole system. For a very large multi-die system, we are talking about millions to billions of mesh elements, depending on the resolution of our simulation. Even if an element spans multiple materials, there are ways to calculate its effective thermal conductivity. That is how we are able to manage large design and simulate real-world heat behavior with high fidelity. We have now seen thermal integrity concerns that span from nanometers at the transistor level to micrometers across multi-die system stacks. But the story does not end here. Once the multi-die system is mounted into a full electronic system, complete with the package, PCB, and even the machine rack, we need strategies to remove heat at the macro scale. This is where air cooling, liquid cooling, and other system-level approach comes into the picture. In short, thermal integrity is truly a multi-scale, multi-physics challenge of multi-die design. Smart modeling isn't optional. It is essential. And bridging data between scales lets designers tackle thermal issues with a divide and conquer mindset. To bring all the ideas we learned from previous course, let's examine a practical case. A high bandwidth memory, or HBM system, with 8 stacked DRAM dies on an interposer. So this system, as you see from the picture, has many 8 stacks that placed side by side to support ultra-high data throughput. Each HBM group connects to the interposer using hundreds of microbumps, critical for both performance and thermal pathways. This architecture is an ideal playground for thermal co-optimization strategies as a demonstration case. Now, let's dig into how mesh resolution affects thermal modeling of such a complicated multi-die system. Here, we use a 10 micrometer by 10 micrometer tile resolution. First, the current data from transistor tiles is converted into a power density contour. Next, metal density at the same resolution helps us derive the thermal conductivity for each finite element within the whole system. By characterizing each SRAM die with this high-resolution data, we can build a stacked multi-die thermal profile that reflects the true heat behavior, not just the averages. All of this came together in a 3D simulation GUI where the designers can actually explore heat flux and thermal contours at real time. The heat flux density here shows how and where heat travels through each layer of the system. The system highlights min and max temperature points to help engineers pinpoint the hotspot and understand where to fix the problem. And animations of the temperature behavior allow teams to assess whether the design stays within thermal specifications or they need adjustment. This visualization empowers a better decision-making process, right from layout to packaging and stacking the whole system.